Everyone knows Fibonacci spirals show up in sunflowers. But did you know that many biological and physical systems, including DNA's spiral structure, display ratios close to Fibonacci values? Even more surprising, astronomers have reported galaxies forming with spirals that echo the same math. Coincidence or a recurring efficiency rule? What we'll explore is not just trivia, but a strong recurring pattern across many systems, suggesting Fibonacci often reappears where efficiency or scaling matters. Today, we'll connect the math behind snail shells, financial markets, and even AI predictions. And by the end, you'll try one tiny test yourself in under 30 seconds using just your phone. Before that, let's start closer to home and look at how these patterns show up invisibly inside your own body. The Fibonacci patterns hidden in your body. At the smallest scale, Fibonacci patterns appear in the very molecule that makes life possible, DNA. In its most common form, called canonical bDNA, the famous double helix completes a full turn in roughly 33.75 angstroms, while its diameter measures about 20.978 angstroms. Divide those numbers and you get 1.6088 within 0.5% of the golden ratio phi. Even more, the spacing between phosphorus atoms along the backbone averages a ratio of about 1.6407, around 1.4% from phi. These close correspondences give scientists pause because they weren't engineered into the molecule. They emerge out of natural chemistry. This doesn't mean every DNA molecule is a perfect golden spiral. The details change depending on base sequence, hydration, or even subtle conformational shifts. Biologists note that approximations within about plus or minus 2% of phi could result simply from geometric constraints, and debate continues over whether the match is a coincidence or a recurring efficiency rule. Still, the numbers remain striking. Life's code often settles into ratios astonishingly close to those that turn up in sunflowers or seashells. Move from molecules to bones and the echoes show up again. Many anatomical studies and popular sources highlight how hand and limb proportions tend to fall near Fibonacci-related ratios. Finger segments, for example, often lengthen in progressions that approximate phi when measured from fingertip to knuckle, knuckle to wrist, and wrist to elbow. Population averages, not every single individual, tend to hover around those numbers. Similar patterns appear in leg proportions. Foot, shin, and thigh often align into ratios near phi, producing balance and mechanical efficiency in walking. These are not literal Fibonacci integers written into the skeleton, but recurring averages that suggest evolutionary pressures favored proportions near certain stable ratios. You can actually test this with a quick experiment right now. Take out your phone and open the calculator. Measure the distance from your fingertip to the knuckle, then from the knuckle to the wrist. Divide the longer distance by the shorter. For many people, the result falls somewhere around 1.6, intuitively close to phi. Not every measurement lands perfectly, but the tendency itself is what fascinates researchers. Modern digital skeletal models refine what earlier ruler-based studies hinted. In 2024, updated simulations confirm that average human bone lengths often cluster near Fibonacci-style ratios. That points away from sloppy measurements or wishful thinking, and more toward repeatable structures that help the body distribute weight, absorb stress, and move with less energy use. Evolution didn't calculate equations, but structures that balance efficiently survive better, and phi-like ratios may represent one of those persistent solutions. The face carries the same suggestion. Across decades, artists and surgeons noticed that spacing between the eyes, length of the nose, and width of the mouth often align with phi-like grids associated with visual harmony. Recent biometric scans added quantitative backing. Attractive and average faces alike often sit closer to Fibonacci-related ratios than random placement would predict. Not everyone falls on exact mathematical lines, but in aggregate, the similarity is hard to dismiss. The sequence seems to influence not just structure and movement, but even how we perceive balance and beauty. Skeptics point out that once you start looking for phi, it's easy to find close enough numbers everywhere. But biology consistently returns to proportions that stabilize growth, conserve energy, and improve survival. DNA must compress thousands of base pairs inside a nucleus without tangling. Bones have to balance load while minimizing material. Ratios near phi seem to help solve those problems. Whether the similarity is coincidence or inevitability, the results speak for themselves. The same sequence keeps resurfacing in places with real functional stakes. Consider walking mechanics again. A leg proportioned in a way that levels forces across thigh, shin, and foot lets the body move with less strain. Over thousands of generations, structures that waste the least energy tend to persist. Evolution doesn't know Fibonacci, it favors what works, and what works often aligns with phi. In this light, Fibonacci isn't a mystical fingerprint left by an external designer, but an emergent geometry that evolution keeps rediscovering. Some researchers suggest that growth itself may generate these ratios. Cells divide, bones lengthen, and tissues expand not through deliberate math, but through chemical gradients and stress distributions. As they scale, patterns settle into proportions we recognize from the Fibonacci sequence. In other words, Fibonacci may describe the mathematics of how natural systems avoid collapse. Each approximation toward phi isn't a perfect law, but a practical balance point. That balance appears at several scales. DNA helix dimensions, bone segment ratios, and even fingertip ridges echo the same geometry. Biology isn't locked into Fibonacci, but it returns to it often enough to raise the possibility of a deeper principle. Instead of elusive perfection, what we see is Fibonacci acting as a favored pathway for growth and form across living systems. It's important to underline, not every body, bone, or molecule is a neat golden spiral. Variability is part of biology and exceptions exist everywhere, but the frequency with which these numbers arise suggests more than random chance. Statistically, we would not expect such consistent clustering if phi wasn't useful in some way. Evolution seems to have stumbled on Fibonacci as a recurrent solution, a shortcut to sustain structures under continuous pressure. The more you measure, the more the same near 1.6 ratios show up. They frame the spiral in DNA's nucleus, the span of your limbs, even the layout of a face. Each discovery ties individual biology back into the same progression seen across plants and patterns of growth. It reframes Fibonacci less as a strange coincidence and more as evidence of a universal tendency, that life gravitates towards specific proportional rules when efficiency matters most. And that perspective leads to something larger. If the code of life carries numbers near phi and the skeleton follows similar scaling, then maybe the same principle extends beyond us. We've already noticed it in flowers and shells, but what happens when you leave Earth entirely? The next patterns push far past biology into surprising corners of the natural world, where spirals shape not only the living but also entire structures of matter itself. From pinecones to black holes, nature's scaling secret. Pick up a pinecone and look at the overlapping scales. If you trace them spiraling left and right, the counts almost always match Fibonacci numbers. That familiar form seems ordinary until you notice the same spiral appears again in hurricane clouds turning above the ocean and even in the arms of certain galaxies. One is something you can hold in your hand, another spans hundreds of billions of stars, but both echo a similar geometry. What connects them is not a single cause, but a shared mathematical shape. The curve itself is known as the golden spiral, a special type of logarithmic spiral. A logarithmic spiral expands outward by a constant factor for every quarter or half turn. It keeps opening at the same angle no matter how big it grows. The golden spiral is one version of this curve, in which the constant expansion factor ties directly to the golden ratio, phi, about 1.618. That's why Fibonacci numbers, which converge toward phi, give rise to a spiral when turned into geometric steps. It looks elegant, but the real key is that such spirals naturally balance growth and spacing. For plants like pinecones or sunflowers, the mechanism behind the spiral is phyllotaxis, the way new seeds or scales add themselves. By emerging at an angle of about 137.5 degrees, the golden angle, they spread out evenly. This placement avoids wasted space or overlap, so over time the spiral becomes visible, balancing biological growth through geometry. It's efficient, nothing is actually counting Fibonacci numbers, but the sequence captures how natural packing arranges itself. Hurricanes arrive at spirals through a very different mechanism. Here, air pressure differences, rising warm air, and the Coriolis effect combine as the storm rotates. That dynamic bends streamlines of air inward until they curve into near logarithmic spirals. The mathematics look similar to a pinecone's pattern, but the drivers are atmospheric physics, not seed arrangement. Spirals again signal systems finding balanced flow, in this case between pressure gradients and Earth's rotation. At galactic scales, the mechanism changes once again. Spiral arms form partly through density waves, angular momentum, and gravitational pull among vast numbers of stars and gas. When astronomers measure these arms, the angles at which they open, the pitch angles, often approximate a logarithmic spiral. Some researchers note that in certain galaxies these measurements come close to golden spiral values, while others stray from them. They aren't exact matches to Fibonacci every time. Galaxies are too complex for perfect symmetry. But the tendency towards spiraling fits the same broad idea. Rotation plus continual outward movement tends to resolve into logarithmic shapes. This distinction matters. Pinecones, hurricanes, and galaxies all show spirals, but for different reasons. Plants spiral for packing efficiency, storms for fluid dynamic stability, and galaxies because of orbital mechanics. The resemblance across these forms doesn't mean identical rules, but it does show how often logarithmic spirals emerge when systems organize themselves. NASA's PHANGS survey using the James Webb Space Telescope produced some of the clearest modern images of galactic spirals. The fine detail astonished astronomers. Arms extend outward with pinpoint filaments, and star-forming regions trace delicate arcs. Analyses compare some of these arms to golden spiral expectations, and in certain measurements pitch angles sit close to phi-derived values. But scientists remain cautious. Not every galaxy matches so neatly. Spiral arms vary according to mass, interactions, and dark matter distribution. The key point is that the family of logarithmic spirals shows up again and again, not that every galaxy hides a perfect Fibonacci ratio. Closer to black holes, spirals appear one more time. Matter drawn toward an event horizon rarely falls straight in. It accumulates into disks, swirling faster as gravity tightens the orbit. These accretion disks often display patterns where the inward pull combined with constant rotation produces near logarithmic spirals. Recent simulations from 2023 onward modeled how turbulence and angular momentum distribute material into these curves. The outcome is not decorative. It reveals how matter rearranges when energy and gravity fight for dominance. Spirals also appear in simulations of giant galaxy clusters, where thousands of galaxies interact in enormous networks. Gravitational binding combined with cosmic expansion applies constraints at scales we can barely imagine. In computer models, the spacing and distribution sometimes approximate ratios tied to familiar Fibonacci-based scaling. Again, this doesn't mean precise golden spirals exist everywhere, but that once structures grow under similar pressures, they often drift toward these recurring arrangements. Why do such different environments keep making spirals? A recurring answer is efficiency. A logarithmic spiral maintains constant shape while scaling up without bounds. That property lets seeds, storms, or stars spread across space smoothly. A fixed angle close to the golden angle when Fibonacci is involved brings balance between growth and existing structure. In biology, that maximizes packing without overlap. In weather, it stabilizes rotating air masses. In astronomy, it spreads stars into clear arms rather than dense knots. The cause is never identical, but the outcome is recognizable geometry. It's worth emphasizing the limits. Not every flower grows on strict Fibonacci lines, not every storm looks golden, and many galaxies deviate, but statistical patterns show a preference. Evolution, physics, and gravitational systems repeatedly land in spirals when balancing forces. The Fibonacci connection makes those spirals measurable, giving us a way to compare very different systems with a shared reference. Scientists highlight this not as mystical evidence, but as examples of how a single mathematical family of curves emerges wherever scaling and rotation interact. Seen this way, the pinecone isn't just an isolated curiosity. It's an easy entrance into a geometry that also governs phenomena as vast as hurricanes and galaxies. The math proves flexible enough to appear in everyday objects and then again in the furthest images captured by space telescopes. Its persistence suggests Fibonacci is more than ornament, it's repeatedly useful. Understanding these appearances today depends heavily on technology. High-resolution cameras and telescope arrays help scientists quantify spirals at galactic scales. Climate modeling sharpened understanding of hurricane coring and airflow. Computational biology refined how plants naturally distribute leaves and scales. At each scale, the same curve rose independently, confirmed not by metaphor but by measurement. This crossover can leave a lasting impression. Think of the spirals carved into a tiny pinecone on a forest floor and compare them to spirals NASA observes billions of light-years away. The vast difference in size is almost incomprehensible, yet our mathematics can describe both in similar language. That's the thread Fibonacci ratios tie together, not because every system copies the same blueprint, but because certain geometries keep providing stable results. That brings us to an important point. The spiral is ancient, but its recognition as a mathematical phenomenon is younger than the mathematics we've inherited. People noticed spiral forms long before space telescopes or hurricane satellites existed. Yet articulating the underlying ratios and showing how they relate to Fibonacci required human insight carried forward in written works. To see how these observations were passed into history and later reshaped mathematics in Europe, we shift from cosmic systems back to the Middle Ages, a period when one man gave his name to the sequence we now associate with all these spirals. The man behind the maths. In the early 1200s, the city of Pisa was a hub of trade and movement. Ships crowded the harbor, carrying spices from the Levant, textiles from North Africa, and ideas exchanged as freely as any goods. In this environment of commerce and calculation grew a boy named Leonardo, the son of a merchant official. History would later remember him as Fibonacci, one of the most influential mathematicians of the Middle Ages. But at first, he was simply a child surrounded by numbers in action, watching how trade relied on systems of keeping track of value. To understand why his contribution mattered, picture the way arithmetic worked in Europe before him. The standard was Roman numerals, those combinations of x, v, and I carved into stone. They looked impressive on monuments but were clumsy tools for daily business. Multiplying or dividing large values with them was slow, sometimes impossible without an abacus, and handling fractions could feel like an endless chore. Outside Europe, though, things had already shifted. Traders in Arabic-speaking regions used a system originally developed in India, the Hindu-Arabic numerals. It used digits 0 through 9, including the 0, which had no real equivalent in Roman numerals. This wasn't just a new set of symbols, it was a framework that allowed faster, clearer, more flexible calculation. Leonardo encountered this system early. His father, Guglielmo, was a merchant customs representative who worked in North Africa. That role exposed his son to places where trade was conducted not in Roman letters, but with this far more efficient numeral system. Traveling with him to the Algerian port of Buja, Leonardo saw merchants performing calculations quickly, tracking interest or exchange rates with relative ease. To a young man trained to see how commerce depended on arithmetic, this difference was striking, almost transformative. When Leonardo returned to Italy, he didn't leave that experience behind. He gathered what he had learned and in 1202 wrote a book that would make him famous, Liber, Abaci, or the Book of Calculation. The work formally introduced the Hindu-Arabic numeral system to Europe. With it, multiplication, division, and work with fractions became manageable on paper rather than only with counting boards. For merchants, this meant reduced errors and faster deals. For tax collectors and administrators, it meant clearer records. Here was mathematics not as abstract philosophy, but as a tool to accelerate everyday life. You can imagine how different calculations looked with this change. A merchant calculating 78 times 42 in Roman numerals would struggle with long, error-prone steps. With Hindu-Arabic numerals, the task was simply 78 times 42, solved much faster. This single shift in representation was like moving from writing on wax tablets to writing on lined paper, with the results instantly clearer. And yet, when Leonardo first proposed it, the change was not automatically welcomed. Some clung to tradition, insisting the old symbols worked well enough. Others were deeply suspicious of zero, which Europeans found unsettling. To them, it seemed strange, even dangerous, to represent nothing with its own symbol. But over time, the advantages spoke louder than resistance. Liber Abaci wasn't written in the style of a scholarly treatise. Leonardo structured it for working people. He filled its pages with examples traders cared about, converting between currencies, dealing with interest, measuring goods, and finding fair exchanges. It was practical math, explained in ways that connected directly to problems people had to solve in their daily business. Hidden among these applications was a sequence of numbers he used as an illustration, not knowing that centuries later this simple example would become his namesake. The sequence itself had been known to Indian scholars many centuries earlier, appearing in discussions of poetry, meter, and combinatorial patterns. Leonardo did not invent it. What he did was fold it into his book as a memorable puzzle, a problem involving pairs of rabbits breeding month to month under ideal assumptions. Start with one pair, assume each reaches maturity in a month, and from then on reproduces each new month. Count the total pairs over time, and you find each number equals the sum of the two before it. The sequence, while not original to Leonardo, stuck in European memory because of how he used it, as a story problem, visual, easy to imagine. This rabbit problem gave the sequence a foothold. It wasn't abstract theory, it was accessible and engaging. Later generations would attach his own name to the numbers, the Fibonacci sequence, and that naming is what carried it forward long after details of trade practices and tax calculations faded. He didn't invent the idea, but because he placed it in asterisk Liber Abaci asterisk, he made sure the sequence was visible to Europe, and from there it spread into wider culture. Leonardo's enduring importance isn't only that the sequence bears his name. His true revolution lay in bridging systems of thought. He drew from Indian mathematicians and from techniques developed by Arab scholars, then connected them to European needs. He passed along both efficient numerals and examples like the rabbit sequence at a time when Europe was ready for new tools. The result was a major turning point. Science, trade, and record-keeping all gained momentum from the adoption of his recommendations. Later advances in astronomy, geometry, and physics depended on that shift. Without it, many forms of Western mathematics would have advanced more slowly. The change wasn't trivial. Roman numerals weren't just on tablets, they were written into laws, contracts, and church accounts. Choosing a new system meant breaking with centuries of tradition. In that sense, Leonardo had to persuade not only merchants, but also institutions that numbers could work differently. Skepticism around zero illustrates the challenge. In some city statutes, the numeral was briefly banned out of fear it could be used deceptively. Yet one by one, practical concerns overcame resistance. Efficiency won over superstition. As this use spread, his influence reached well beyond his own city. Accounting, banking, and early financial systems adapted his methods. Over time, the structured mathematics he advocated supported not only trade networks but also the flowering of Renaissance science. Every architecture calculation, every navigation chart, every astronomical model built on the numerals he had promoted. So while the rabbit sequence still bears his name, perhaps his most decisive contribution was building Europe's gateway to the numerals that underpin scientific progress to this day. The key lesson from his story is how practical needs and deeper mathematics weave together. Leonardo wanted to solve the concrete problems of merchants and customs officials. By teaching them a more efficient way of handling numbers, he also unlocked patterns that reached far beyond commerce. The sequence that later captivated botanists and artists was, in his book, simply a teaching example. But once released, the sequence became a link between calculation, natural patterns, and abstract math. That connection has kept his name alive across centuries. What makes his legacy especially clear is the role of cultural exchange. None of the ideas he wrote down originated entirely with him. India had provided the sequence long before, and the Arabic-speaking world had refined the numerals he borrowed. Leonardo's place in history comes from being the bridge, the man who carried those ideas into Europe, wrapped in explanations merchants could use. That transfer changed the course of mathematics and put his name on one of the most recognizable series in math today. So when people say Fibonacci, they aren't referencing a solitary discovery. They are naming the man who translated and transmitted. He made mathematics a working tool for his generation and ensured ideas from far-off places became part of European knowledge. His book Liber Abaci published in 1202, introduced Hindu-Arabic numerals, included the famous rabbit problem, and set the stage for centuries of exploration. He didn't invent the sequence, but his book made it visible, and later generations began seeing that same progression reflected across nature. And that takes the story to its next step. Because once a simple list of numbers exists, people cannot help wondering, why do these abstract values surface again in seashells, storms, or galaxies? What connects a line of digits on paper with spirals visible across the world? When numbers become spirals. To see how the numbers themselves generate spirals, you need only follow the math step by step. Begin with the Fibonacci sequence, where each term equals the sum of the two before it. If you divide one number by the one before it, say 21 divided by 13 or 34 divided by 21, the ratios gradually close in on a single value known as phi, about 1.618. The farther along the sequence you go, the closer the ratios get to phi. This steady convergence is why the sequence links so strongly to proportional patterns we see elsewhere. Now translate those numbers onto a drawing. Take squares whose side lengths follow consecutive Fibonacci numbers. Start with one, then another one, then two, then three, then five, and so on. Arrange each square beside the last so they build into a growing rectangle. Once those squares are in place, connect quarter circles across them in order. The arcs merge into a curve that approximates what's called the golden spiral, a specific form of the more general logarithmic spiral. In just a few moves, you go from a numerical list to a curve that looks exactly like forms embedded across biology and physics. The golden spiral matters because it never changes its shape as it scales. Logarithmic spirals have this defining property. The curve expands, but its angle remains constant. Whether small or vast, the spiral keeps the same profile. This self-similarity explains why so many structures approach it. If a system grows by a fixed proportion each step, a chamber of a shell, a ring within a flower head, a new unit of growth stacked on the old, the outcome is a logarithmic spiral. The Fibonacci sequence simply encodes the proportions needed to generate one form of it, where phi sets the scaling. In seashells, each new chamber must be big enough for the animal to fit inside, yet still shaped so the shell remains balanced. A constant percentage growth rule makes that possible, and the shell's edge then traces the familiar spiral. In storms, airflow driven by pressure and rotation balances forces into near-logarithmic curves that hold the system together. In galaxies, stars orbiting a dense center spread outward in arrangements that often resemble logarithmic spirals, though not every galaxy matches perfectly. What links all of them is proportional scaling. Units change by consistent ratios, and the spiral emerges naturally from that process. Scientists use digital tools to verify this connection in fossils too. Reconstructions of ancient ammonites show that many shells align closely with logarithmic spirals. The fit can be measured by equations and repeated across species that lived across different eras of geologic history. These studies confirm the spiral pattern isn't coincidence or human projection. Like modern shells, the growth laws in ancient creatures produced curves that matched mathematical expectations. The spiral isn't designed from the outside, it comes from how proportional growth stabilizes form. Computer simulations make the principle easy to test on any system. Start with a simple rule: at each step add a new unit scaled by a constant factor. Plot these steps as dots, then connect them. The result bends into a logarithmic spiral every time. The idea doesn't depend on whether the dots represent cells, seeds, orbits, or molecules. The rule alone generates the pattern. That universality explains why spirals appear wherever systems grow incrementally under proportional constraints. This also explains their resilience. Unlike circles or ellipses, which distort if growth overshoots or undershoots, a logarithmic spiral can absorb irregularities while keeping its basic shape. That built-in stability means evolution and physical dynamics return to it repeatedly. Spirals show up not because every natural system chooses Fibonacci, but because proportional scaling tends towards spirals, and Fibonacci ratios approximate the needed constants so well. Many spirals end up close to the golden spiral without hitting phi exactly. The similarity alone underscores how often these rules apply.